Hello class, and thank you for watching. In this video, the learning objective is students will compare the rate of change of 2 points using the average rate of change near those points. Students will describe how two quantities vary together at different intervals of the function. Now, we're going to start today's lesson by discussing instantaneous rate of change. The rate of change of a function at a particular point is the rate that the function would change if the function changed at that specific point. Now, the concept of this is referred to as instantaneous rate of change. How fast is the object moving on this graph right here? How fast is the function moving at that location there? While we cannot find the rate of change at a particular point, at one specific point in this course in AP Pre-Calculus, we can do the following two things. We can estimate again how fast the object is moving right here by using 2 points and very small intervals, 2 points that are very close to it. We can also compare the rates of two different points by estimating individual rates of change by using the concept of what's referred to as a tangent line. So this line right here that I'm highlighting is referred to as the tangent line because it's only touching the graph at this one location. And second, it is perpendicular again to the velocity of this thing right here. So this line, the slope of this line correlates to the speed in which this dot here is moving along again this curve. How fast is this point moving along this curve right there? So while we can't do this again in pre-cal, what we can do is give it an estimation by picking values very close. So in this example right here, since our x value is -4, I can pick values that are very close to that -4. For example, I can have the interval be -4.5 and -3.5. Values that are very close. Those are going to be my x1 and x2. So to estimate the slope of this line and to figure out how fast this graph and to figure out to estimate the slope of this line and to figure out how fast the graph is moving at this location, I can use again this x1 and this the x2, which is going to be again in between. It's going to be an equal distance from this location of -4. Since this is the function up here, since this function is represented by this graph here, I can use this as my x1 and x2 to figure out what the y value is. So let's evaluate this. So if I plug into this function, this is my f. If I plug in -4.5 into these values of x, and again I'm going to use the calculator to do this, I'm going to end up with a number of 1.33875. Okay. Now remember, in order to figure out the average rate of change, I need again 2 points. I need a x1 and a y1, which I already know. My x1 is -4.5 and my y1 is now 1.33875. Now I'm going to use another point again to estimate this slope. So I'm going to use a point, like I said, the points very close. Let me do it in blue so it could stand out. Right here and this point right here. And I'm going to figure out the slope of this blue line right there. Okay, it's not the red line, but if I use points very close to that red line and points again to the left and to the right of that one location here, or that one pot, I can estimate the slope of that red line. So now I'm going to use the value of -3.5. And remember, I'm plugging this number into this x right there, okay, because that's what f of x is. So I'm replacing x with -3.5. And I get the number 2.75625. So now I can figure out my average rate of change by getting the y2 value. This is my y2 and my y1. So if I get the y2 value, negative 3.5, and I subtract the y1 value, f of negative 4.45, which again are equal to these numbers right here. This number is this, and this number is that one. I'm just using this notation because I don't have enough space to write those decimal values there. And I'm going to divide it by the x2, which is negative 3.5. And I'm going to subtract it by the x1 value, which is negative 4.5. We get the following. And remember, I'm plugging this into the calculator. So what I plugged into the calculator is, for this, I plugged in that number, and I subtracted again the f of negative 4.5, which is this number right here. So I did this minus that, and I divided that by negative 3.5 minus negative 4.5, my x2 minus my x1. And we get the number 1.4175. Okay, so the slope of this blue line, let me highlight it. So that's what the slope of this blue line is. This blue line has a slope of 1.475, which means that the slope of this red line is going to be very similar to that. Okay, it's going to be a very close approximation to the slope of that one line right there. And the thing I want you to understand from this is that this slope, by looking at the slope of that line right here, let me just now focus on this right here, on this line here, on this red line here, correlates again with what's happening with the graph. If I look at this graph right here and I break it apart, and I break it up into intervals where my max and minimum value is occurring, notice that in this location right here, my graph is going up. And look at what's the rate of change is. The rate of change is a positive number. So it correlates. If my function increases, if f of x increases, then that means that the average rate of change is going to be positive. It's going to be a number that is greater than 0, which it is. We saw that it's equal to 1.4175. That number is greater than 0. It's positive. And this is what's useful about using, again, this and estimating what the slope of this tangent line is. Like, for example, let's continue with this trend and this idea that if I look at this point right there, I am not going to be able to determine, let's do a different color. I'm not going to be able to determine how fast I am moving at this point right here, at this brown point right there. But what I can do is pick 2 points that are close to it and figure out what the average rate of change is between those. The closer, the more accurate I become. In this example, I'm not going to be too accurate. I'm not going to pick points really close to each other. I'm just going to pick something that will give me a nice value. So I'm going to pick -2 and 0. Okay. So I'm going to figure out what the average rate of change is between those 2 points right here. So for this one, my x1 is going to be -2, and for 0, my x2 is going to be 0. So let's figure out what the y1 is going to equal by plugging in -2 into this function here, into the x's of this function. So plugging in -2 into our function, we end up with a value of 2.52. And now to figure out the y2 value, I'm now going to plug in my 0, which is going to equal to 0. Now to figure out the average rate of change of this line here, the arc, I'm going to do y2, which is f of 0, which is 0, minus y1, which is f of -2, over my x2, 0, minus my x1, -2. And again, I'm using this notation here just because I didn't want to write the decimal value of 2.52 and I don't want to write the 0. So I'm just using that notation. But remember, this means 0 and this means that. So in the calculator that says right, I'm writing 0 minus this on the top, and I'm going to divide it by 0 minus -2. And that gives us an average rate of change equal to negative 1.26. And look at that. Look at that value right there, okay? Notice that in this portion of the graph, you'll notice that the graph is again decreasing. And where it's decreasing, notice that the average rate of change is now a negative number in that portion. So we can approximate that the average rate of change, let me erase this, that the average rate of change of the line that intersects only at this location right there, at this dot right there, is going to be approximately this value there, which means that at this location, let's call it point B, and we'll call this one a point A, that at point B is moving at a rate of negative 1.26 meters per unit, whatever the measurement is, okay? So negative 1.26 meters per time, whether that's time is minutes, hours, whatever, but it's moving at that velocity, at that speed. That is the rate of change, which correlates because the graph is going down. Notice now that it is a negative number and not a positive number like the previous example. Over here, it was greater than 0, and now it's less than 0. So we can correlate this concept that if the function is decreasing, if our function is going down, then that would give us that the average rate of change has to be a number that is going to be negative. And if you remember the investigation that we did in class today, that correlates again to the concept that we have here. Notice that we are concaving downwards. This graph, let me do it in yellow, its graph is concaving downwards. So we investigated today that if the graph is concaving downwards, then that means that the rate of change is slowing down, it's decreasing. And that makes sense because from a positive number to a negative number, it's changing again and becoming smaller. So it's decreasing in size. So that's another thing that we can pick up on this. That if f of x concaves down, then the average rate of change is decreasing. It's going from a larger number to a smaller number, from 1.47 to negative 1.26. That's a smaller number. And let's investigate this one more time, and let's see what happens at this location here. We'll do in gray at this point right there, okay? So let's figure out what the average rate of change is right there. And this time I am going to use a number that is closer. We're going to use the 0.5 for x1 and 1.5 for x2, since we want to see what's happening right here at 1. So I cannot figure out the slope of the tangent line. I can estimate that value by picking 2 points close to it. Okay, so let's figure out what the average rate of change and estimate the instantaneous rate of change at 1 by picking 2 points close to it. So we're going to pick the number 0.5 and 1.5. We're going to obviously get closer and get like really close and pick 0.99 and 1.001, but this again is good enough, all right? Because all we're just going to get a rough estimation of this. So let's see. To figure out the average rate of change, I find my y1 by plugging in 0.5 into my x. And again, I'm just going to use the calculator for this, and that gives us a total of negative 0.67375. And the y2 we evaluate by plugging in 1.5, and that's negative 1.70625. So our average rate of change will get f of 1.5, our y2, minus our y1, f of 0.5, divided by our x2 minus our x1, which equals to a negative negative 1.0325. And that makes sense. Again, that correlates to what was going on in that section of the graph. In this section of the graph, again, the graph is decreasing, is going down. So it makes sense that at this point, the average rate of change will be approximately 1.035, specifically negative because it's going downwards. So the approximation value should also be negative. Again, which correlates to what we had written earlier, that if the function is decreasing, then the average rate of change has to be a negative number, has to be less than 0. So it has to be negative. And again, that's exactly what's going on there. Now look at what's going on right here. Negative 2.26 is smaller than negative 0.325. And the reason for that is because of the concavity. It's starting to curve upwards. And when the graph starts to curve upwards, again, as we investigated earlier today, that means that the average rate of change is not decreasing anymore. It starts to increase. So hence, this is why our number changed from a negative 1.26 to a negative 1.0325, because it's becoming a larger value. And if I look at the rate of change at this location and at this location, I would see that these rate of changes are going to be bigger than this one right here. Now, while we're not going to do this one because we already know what's going to happen here, we're going to end up with a positive value, all right, because the graph is going up, just like we saw right here in red. I do want to talk about this one. At minimum points and at maximum points, the average rate of change of those locations is always going to be 0. Because the graph is not moving up or down anymore, this point, again, has no velocity. It has no rate of change that's going to be positive or negative because it's not moving at 0. It's basically a car that's being parked. It has been stopped. So think of your speedometer. Your speedometer would be at 0 if you're not moving anymore. You're traveling at 0 miles per hour. So at those locations, the tangent line will always be horizontal. And I'm going to do that using a blue line. So at this location, the tangent line will be blue. And at this location up here, the tangent line will be blue. Okay, so, and write this is important. The average rate of change at extremus, I'll write it at extremus because that correlates to maximum and minimum values, is always 0 every single time. So we don't need to do a calculation and estimate what that value is. That by default is always going to be 0 because the graph is not moving up or down anymore. So anywhere we find a maximum value or a minimum value, the tangent line that only touches that location is always going to be 0, which means that at that location, the average rate of change at that specific point is always 0. Okay, now let's go on and let's discuss again the correlation, just what we talked about, the correlation between the rates of change of f with the graph of its function. And as we discovered, and again we just reviewed, if the rate of change is a positive number, just like in this example right here, the arc is a number that's greater than 0, then that means that the function is increasing. This is biconditional. This correlates and goes in both directions. If the function is increasing, then that means that the arc is greater than 0, and vice versa. If the arc is greater than 0, then that means that the function is increasing at that location. And if the function is decreasing, then the arc is going to be a number less than 0, and vice versa. If the arc is less than 0, then the function is decreasing. That's exactly what this is referring to. And like we discovered in today's activity, in today's class assignment, if our rate of change is increasing, if the arc is changing along an interval and becoming bigger and bigger and bigger, that means that the graph is concave upwards, and the other way around as well. If the graph is going to concave upwards, that means that the rate of change is going to be changing to larger numbers. And then the opposite situation, if the rate of change is decreasing, then the graph is concave downwards. So like in this example right here, this is a graph that is increasing. The values of y are getting bigger and bigger and bigger. So here, let's write this down. F increases. Since f increases, that means that the arc has to be a positive number. So if I find 2 points and I connect them with a line, I can see that this will create a line that goes in a upwards direction. So that means that the slope, again, which is the same thing as arc, the arc of this, the average rate of change, is going to be positive. Okay, don't confuse arc with something else. I'm abbreviating the word arc, average rate of change. So slope, the slope is going to be positive. Now, because the graph is concaving downwards, okay, that means that your arc, your average rate of change, is decreasing as a result. Let me move it over here. So your average rate of change is decreasing as a result. And that makes sense again because I look at more points, like if I get another arc, another average rate of change, look at the steepness of this line. And again, this is exactly what we correlated and we talked about in today's class activity, class assignment. And if I find another arc, like right here, I notice that the steepness isn't as steep. So we go from very steep to less steep. So that's because the average rate of change is getting smaller and smaller. So our arc is decreasing. And now if we look at this graph, the graph for G, this graph is decreasing. It's going downwards from left to right. So since G decreases, then that implies that the arc is going to be a negative number. No matter what 2 points I use, whether I use this point, let me do it in black first, where I use this point and this point, I'm going to see that those points connect with a line that's going downwards. So your average rate of change is negative. And since this again is concaving upwards, then that implies, since G concaves up, that implies that your average rate of change is increasing. So if you look at this, yes, the steepness is going to become smaller, but it's becoming less negative. So for example, this right here is very steep. This has a very negative steep slope. But when I look at 2 other points, let's say I look at this point right here to this point right there, from here to here in red, is not as steep, so the number is not as negative. And if I look at this point to this point, it's still going to be a negative number, but not as negative. It's going to be even a smaller negative number, which means it's bigger in value. So the average rate of change is increasing. So let's fill in the blanks that we have here in this example. The graph of f of g are shown above. Let's complete the blank to correctly describe the graph of f and the rate of change. Well, the rate of change is, like we said for f, is going to be positive because the graph is moving upwards. So the graph is going to be positive because the graph of f is increasing. So why is it positive? Is because again it's increasing. That's why. Now, is the rate of change of f increasing or decreasing? Well, like we mentioned earlier, it's decreasing. Your arc is decreasing. And the reason for that is because of its concavity. It's concaving down. And for g, well, the rate of change is either going to be positive or negative. Well, again, if we look at this, the graph is going downwards. So your rate of change is going to be negative. And again, because of the reason I stated earlier, because it is decreasing. Now, is the rate of change increasing or decreasing? Well, that has to do with concavity. Our arc is increasing because it's concaving upwards for g. So since it concaves upwards, that means our rate of change is increasing. So here, it's increasing because the graph concaves up. Now let's compare some rates of change. Let's look at this situation right here. Okay. Which of these two graphs is going to have a larger rate of change? So we look at these examples right there that we see right here. Let's compare these. Now, when we look at this, because this graph on the left, the graph of f again is increasing, that means that the rate of change is always going to be positive. So our arc is always going to be a number greater than 0. And for this example right here, because on this example right here, because the graph is going downwards from left to right, that means that regardless of any point that I pick, again, our arc is always going to end up being a negative number, as explained as before. So if I pick this point as my x1 and I pick that point as my x2 and I connect it with a straight line, notice that this line again decreases. So that's going to result in a rate of change that's going to be a negative number. Think about the equation of this green line. Y is equal to mx plus b. The equation will look like this, and the value of m would have to be a negative number in order for the graph to go downwards like this, for the line to go downwards. So again, m correlates to average rate of change. But if I look at this one right here, and I get 2 points right there, and I connect those 2 points with a straight line, again, since the equation of a straight line, like over here, is y is equal to mx plus b, the value of m, again, has to be a positive number. And the slope, m, again, correlates to the concept of average rate of change. It's the same concept, but we're using the word average is because these things are not constant. Slope refers to the idea that it's going to always be the same number. But this slope right here will be different if I pick another point, like for example there, okay? So in terms of which graph has a larger rate of change, well, that will obviously be this one, because positive numbers are bigger than negative numbers. So f will have a bigger value there, okay? So let's write that down. Sorry. When will a function, sorry, I don't want to ask it as a question. Sorry, I'm getting all tongued up, but I have it correct now, okay? A function has a larger rate of change where it increases. This is the where it increases over where it decreases. Okay, that's a very important part of this lesson right here, and the basic understanding again of this course. Now you need to be very careful in answering questions about graphical behavior, and you need to pay close attention to the wording for each statement. Does the graph again, or does the question refer to the graph of f, or does it refer to the rate of change of f? So that's the key thing that you need to pay very close attention to when answering questions about this. And then of course is the same thing the other way around. A function has a smaller rate of change where the graph where it decreases over where it increases. So any part where the graph is increasing, that rate of change will always be bigger than places where the graph is decreasing, because the rate of change of there was going to be negative every single time. So let's look at this situation right here. And we're only going to worry about A, B, and I'm sorry, A, C, and D. Don't worry about B here, okay? Now at point A, well, let's split this up. The first thing we're going to do is identify, again, make the correlation of how the rate of change, what the rate of change is going to be at those different locations. At this location of A, of C, and of D. So we're going to start by breaking this apart and see what's happening in those sections. So I'm going to draw a vertical line here because this is where my maximum is. I'm sorry, my minimum value is right here. And right here is my maximum at that location of D. And we see that in the first section, in this section, okay, which I'll highlight in blue, I see that the graph is decreasing. In this section in red, I see that the graph is increasing. And in this section, I'm going to highlight in purple, I see that the graph is decreasing. So the graph of the function j is shown above. Use the graph of j to determine at which point j has the following behaviors. So we're looking for where the rate of change of j is going to be positive. Well, it's going to be positive at which of the points that we see here? Well, it's going to be positive wherever the function is increasing. And we see that at point C, okay, and at point B, obviously also, the graph is increasing. So we're increasing from -3 to positive, I'm sorry, from +3 to +8. This is all on the positive side. +3 to +8. Where's the rate of change of j a negative? Well, in order for it to be negative, that means that the graph again is decreasing. And it's decreasing again in this blue section and in this purple section. The blue section is from the x values of 0 to 3. And from 8 to, well, infinity. We'll say infinity because we're not assume that it's going to continue. All right. So let's draw an arrow right there and assume it's going to continue. So from 0 to infinity. And now, which rate of change is going to be the largest? So that's where we're going to use the points. Is the rate of change going to be the largest at point A, at point C, or at point D? At point D, you should automatically know, because this is a maximum, again, like we wrote earlier, this is going to have, at point D, at D, the average rate of change is going to equal to exactly 0 because it's an extrema. And that's going to be true every single time. At every place we have a maximum or a minimum, that's going to equal to 0. Okay. Now, since our function is decreasing, the average rate of change of A is going to be negative because, again, this is going to have a tangent line that if I connect this will have a tangent line that will be going downwards. So at A, your average rate of change is less than 0. So it's going to be negative, less than 0. And the reason for that is because the function is decreasing, because J decreases in that interval. And at point C, this point right there, at C, your average rate of change, that's going to be a number that is positive, a number greater than 0. And the reason for that is because the graph is increasing in that interval. So having that information all collected and all put together, well, which one is going to have the largest rate of change? Well, obviously a positive number is bigger than a negative number. Now, we didn't calculate what the average rate of change was at A, nor at C, nor at D. Well, at D we did because we know that's equal to 0. But we didn't determine what the actual number was for C, and we didn't determine again what the average rate of change estimated the average rate of change right here at A by picking numbers really close to it. But because the graph is going down, I know that the average rate of change for A, or in the estimated value for the average rate of change of A, is going to be a negative number. And since negative numbers are smaller than positive numbers, I know this one is going to be bigger than A. So that whatever the average rate of change is right here for C, that's going to be bigger than whatever this number is over here at A. And since a positive number is bigger than 0, obviously this could be just 0.1. 0.1 is automatically bigger than 0. Any positive number is always bigger than 0. That means that this right here is going to have the largest average rate of change. So point C has the largest rate of change. Okay. Now, if we were going to look at all 3 points and look at this value right here, we would then have to, at point B, we would have to now consider the concavity. While at point B, the graph is increasing, this is also going to have a positive rate of change, and this one is also going to have a positive rate of change. But which number is going to be bigger? Well, since this is concaving upwards, the average rate of change is going up. It's increasing from a negative to a positive value. And since this one has a concaving downwards, it's going to have a negative rate of change. I'm sorry, the rate of change is going to be decreasing. So it's going to become positive to 0, and then over here it's going to become negative. So you see, it's decreasing in value. So the only way to figure out which one is going to be bigger is by then estimating what those values are. And we'll still see again in terms of the steepness, this one right here would be steeper than if I pick 2 points to estimate that one right there. So this one right here will still be bigger. But in terms of these 3 points right there, which is what I'm focusing on, again, this one right here will have the largest rate of change because since it's increasing, this will have a positive rate of change. This point right here will have a negative rate of change, and at the maximum, that rate of change is always equal to 0 at extremis. All right, so that concludes again our notes for today. Again, thank you for watching. If you have any questions, please don't hesitate to ask. And like always, I hope you have a great day. Goodbye.